I shortly introduce Professor Francois Boulier. It's my great pleasure to introduce him to you. He's actually a professor at the University of Lille. I can say Lille is a beautiful, historic, and modern city in the north of France. I invite you to visit this beautiful city if it's possible for you. Francois got his PhD in '94 from this university, but I think at that time it was University of Lille 1. And his main research area is differential algebra, and he's known as one of the pioneering researchers in this field. His work includes not only the theoretical aspects of differential algebra, but also the applications of these topics in mathematics, in biology, and also in other domains. And also I can say that in this direction, he developed Maple and Python packages for computational purposes in differential algebra. Today, Francois will talk about the link between the fundamental theorem of tropical differential algebra and also, in other side, the numerical integration of ODEs. So we are grateful to Francois for accepting our invitation, and so I invite him to start his talk. Please, Francois.
Thank you very much, Amir, for this nice introduction. I've never been in Iran. I think it's the first time I talk to Iranian people, so unfortunately it's a bit yeah. I wish I would be in Isfahan, but okay, it will be for another time. It's not so easy right now to travel. So the talk covers at least 3 topics, so which is quite a lot. So I will give the ideas of many things, but not enter too many details, and I will proceed backwards. I will start from numerical integration, then switch to tropical differential, and then go back to tropical differential algebraic geometry. And in the between, I will go through an important paper of 1984, and that we will see here. So somehow we have 3 topics here. So I have a running example, which is very classical problem that most of you may know, but it's the brachistochrone problem, very well explained on the Wikipedia. So you assume that you have 2 points A and B in the vertical plane, and you fix a curve. You have a particle moving from the point A to the point B, following a curve, and we choose the curve. Initially, you assume a few things like the speed is 0, there is no friction, and the particle is only subject to the gravitational law. And this very old classical problem is to find the curve, the trajectory for the particle, such that the particle arrives at B as soon as possible. So it's a very classic. There are many different ways to solve this problem. It's very well explained on the Wikipedia. And one way to do it is through ODEs. So on this slide, I don't know if I'm wondering if you see my mouse. Yes, you should see it. So you can.
Yes.
Yeah. Okay. Thanks. So you can encode this the ODE. I've written it in some implicit form. It's what Reed and Kolchin, who founded the differential algebra, would call differential polynomials. So it is implicit because it is not solved with respect to y prime. And so the ODE is written here. The solution is known to be a cycloid. So like this one. On the former slide, it would be the blue curve, which is here. The fastest one is this one. And if you So you have a not so obvious solution, which is a cycloid. And there is another solution that you can see also, is that the constant function y of x equal to 1, the constant function 1. And if y is equal to 1, then dot y prime is equal to 0. And you will, so the first term will disappear. You have 1 minus 1 equal to 0. So the constant function 1 is a solution. And this function touches the cycloid at this point, when y is equal to 1. And if you are used to numerical integration, I guess most of you are, you can, I think you will feel that you will have two problems for numerically integrating this ODE. One at the origin, looks like a painful problem for numerical integration. So for the initial value, y0 is equal to 0. And we will have another problem at this point where y is equal to 1, because two solutions are going through that point. So if we were solving this ODE numerically with a classical integrator, numerical integrator, we would, the first thing we would do would be to transform it into an explicit ODE. That would be the ODE, the formula 1. So y prime is equal to f of x and y, with f being this square root of 1 minus y over y. And already we see that for the initial value y0 is equal to 0, a numerical integrator could not even start, because you would have a division by 0. And for y0 is equal to 1, we see that the dot y will be equal to 0, which is consistent with what we saw on the curve. But if you know the classical numerical integration theory, you see that in this at this place, the ODE does not satisfy the so-called Lipshitz condition. This partial derivative, df over dy, becomes infinite, and then the theorem which tells you that there exists a unique solution in the neighborhood just does not apply. And which is true actually, since we have two solutions at this point. And if you take a basic numerical integrator, the more complicated one, it's more complicated to know what they would do, but for a basic one, it would just, if we start at y0 is equal to 1, it would just follow the constant function y is equal to 1, and not the cycloid. You can make the numerical integrator follow the cycloid, but then you have to prolongate the ODE to differentiate it some more times. And somehow this means that you have to add some further initial values. And we will see that later. Okay, so this is in numerical integration. Let's have a look to the implication in terms of formal power series. So there is a very strong connection. Actually, for some of you who know numerical integration, it's clear, because if you design, say, a Runge-Kutta method, the first thing that books tell you is that, okay, you have a formula, you can compute the Taylor expansion of the Runge-Kutta formula, and compare it with the Taylor expansion of the true solution. But it's the basic starting point when you try to design a Runge-Kutta scheme. But this somehow assumes that the Taylor expansion of the true solution exists and is unique, which is not the case here. So I'm coming back to my implicit ODE, so in implicit form, to my differential polynomial. I'm looking for a formal power series solution y double bar. So the numerical value will be y0, y1, and y2. They appear as a coefficient in this series. So for y0 is equal to 0, actually, there is it's easy to see that you have no formal power series solution of your ODE. However, there exists formal Puiseux series solution. If you allow fractional exponent, 2/3, 4/3, and so on, there is a solution. And this solution is actually quite useful to exit from the singularity. If you want to really start at 0, you can make one step with this Puiseux series and then go on with a numerical integrator. So it's very important to have such series in practice. And for y0 is equal to 1, there are two formal power series solutions starting at 1, and you can distinguish them with this minus 1/2 coefficient for y2. But that, if you want to use that, you have to provide more than one initial value. Okay, so let's a bit FPS are formal power series here. Let's survey a bit what's going on in this area. So I mentioned differential algebra. Differential algebra is an algebraic theory which was designed by Ritz in the first half of the 20th century. It's an algebraic theory for systems of differential polynomials, and it covers as well ODE or PDE. ODE actually are particular cases of PDE, since they're really handled like that from a purely algebraic point of view. And one student of Ritz, Ellis Kolchin, developed further the Ritz theory and wrote this famous book, Differential Algebra and Algebraic Groups, in 1973. And in 1950, it's the main book of Ritz, a few years before he died. I will not need many notations, just this one. So differential polynomials, we have seen one with the implicit Brachistochrone ODE. They are supposed to belong to differential polynomial rings. This is Ritz notation. So F would be the base field. In our case, that could be the field of the rational number. It should have a characteristic 0. Rational number, real numbers, complex numbers. And yy up to yn are the differential indeterminates. Somehow they are the unknown functions. So there are two problems we can consider. The first one is this one. Assume you are given a system, so finitely many differential polynomial forming a system sigma, and assume you are not given the initial values. And the first problem is this one. Since you are not given initial values, does there exist somewhere, does there exist initial values for which the sigma has a formal power series solution? This problem is not can actually be solved by the classical differential algebra tool. It is decidable. There are algorithms to solve that. It amounts to differential elimination. I will not talk about that. That would be another talk. And it is solved as well for ODE and for BDE. There are many software a few software implement such methods. Since it's my talk, I mentioned the differential algebra Python package, but there are other packages in Maple actually. So this is the first problem. And the second one is this one stated here. So assume you are given a differential system sigma, finitely many differential polynomials, and initial values. So I give you the system and initial values. But the question is, does there exist formal power series solution for sigma and these initial values? The problem actually is not addressed by Ritz and Kolchin in their books. There is a very important paper by Jan Denef and Leonard Lipshitz, not the same Lipshitz as the one we talked first. This one is from the 20th century, the other one is from the 19th century. So entitled Power Series Solution of Algebraic Differential Equation in the Mathematische Annalen. And it's a wonderful paper. And they prove that this problem cannot be solved in general for PDEs. The assumption that there exists an algorithm for solving this leads to something paradoxical. Somehow they managed to encode Hilbert's 10th problem in this problem. For ODE, the problem is decidable, but we are really on the edge of decidability. And actually, the existence problem, okay, there is an algorithm you can implement. It was never implemented. You could, but if you implement it, it will tell you that, okay, for those initial values, there exist formal power series. But if you want to find out if there are non-zero formal power series, the problem becomes undecidable. You can't solve that in general. It was this relies on a result by Michael Singer in 1978. So what I will do in the next slide is to enter a bit in this Jan Denef and Leonard Lipshitz methods, how they do that. And we will see that this is related to tropical differential algebra. So we consider a differential. So we enter the Denef and Lipshitz paper. In this paper, to say it simply, you consider a differential polynomial P, say of order n, in one differential indeterminate y. They generalize afterwards. But for the moment, we only have one differential indeterminate, so one unknown functions. The coefficient might be formal power series also. And we are concerned by the existence problem of solutions for prescribed initial values. The second problem we are considering, the difficult one. And if you remember the Brachistochrone problem, for initial value y0 is equal to 1, we had to add some more initial values to really solve, and sometimes you may need to do that. So actually, in general, the number of initial values you need to really state the problems depend on the initial values themselves. You don't know in advance how many initial values you will need. So it looks a bit unrealistic, but actually we can turn it into something realistic, but from a mathematical point of view, it's better to do it like that. Let's assume that we have infinitely many initial values. And let's encode them into a formal power series. So I will call this one an initial value encoding series. So y with a single bar give me my initial values, y0, y1, y2, and so on. So I have my ODE, I have my initial value encoding series y bar, and what Denef and Lipshitz provide in their paper. And for this, they relied on a paper by Hurwitz in 1899, a very important formula. They provide a method to compute two integers. I call them beta and delta, whatever, two exponents, two bounds actually. And the statement is this one: if P of x y bar, so y bar is the initial value encoding series, remember. So if P of x and evaluated over the initial value encoding series is equal to 0 modulo x to the beta, then there exists y bar bar, formal power series, such that y bar bar is a prolongation of y bar, starting at x at the exponent delta. So the delta first initial values of the delta first coefficient of the two series will be the same, and P of x, y bar bar, and so on is equal to 0 modulo nothing, means that y bar bar is a solution, really a solution of the ODE. So it's a bit complicated. Let's explain this. So a slide of explanation, and then I have a few slides on with examples. So the explanation fits on one slide, if you admit the formula, the explanation of what's going on. So consider an ODE P. I have taken it at order 1 to make things simple, but everything generalized. You have y bar, the initial value encoding series, and there is a fact. Everything lies in this formula actually. If you evaluate P replacing y by y bar, you get a series, with some coefficients that I call P0, P1, P2 over 2, and so on. And those expressions P0, P1, P2, they are denoted here. We will see examples on the next slide. P0 is the ODEP evaluated on the initial values. So evaluated, it's a number. So you replace x by 0, because we are looking for series expanding from the origin. You replace y by y0 and y prime by y1. So you get a polynomial expression in the initial values. Here. P1 the same. You have to use more initial values. So y second is replaced by y sub 2, and so on. And what does this slide show? It shows first that, well, if you have an ODE of order 1, you provide more than one initial value. You cannot choose all the initial values freely. There will be constraints on the initial value. They must satisfy some polynomial a system of polynomial equation, because they must satisfy. If you want P to be 0, you want P0 to be 0, P1 to be 0, and P2 being 0, and so on. So Y0, Y1, Y2, Y3 must annihilate this system. And the second thing you see also, which explains a bit the notation of Denef and Lipshitz, saying that Y0, Y1, Y2, Y3 annihilate P0, P1, and P2, this polynomial system is saying exactly the same as P of x, y bar, and y bar is equal to 0 modulo x to the 3. If you only keep the 3 first terms of this series here. These are just two different ways to say exactly the same thing. So I don't know if my explanation is clear. Maybe it's simpler over an example. So the Brachistochrone ODE. So P is the Brachistochrone ODE, and I've taken a generic series Y0, Y1, Y2. So if I define, how do I compute P0, P1, P2? I do it like that. So you take P and you differentiate the differential polynomial P. So you have P prime, P second, and so on. So if let's do it just a bit. If you differentiate y times dot y to the square, you have y prime to the cube. You find it here, and 2y, y prime, y second that you find here, and so on. So you can just processing like that the differential polynomial, you can generate infinitely many differential polynomials. Then, I'm playing with my slides, you replace y by y0, y prime by y1, y second by y2, and so on. So you get this polynomial system. Now, let's have a look to what's going on for the initial value y0 is equal to 1. So if y0, if you prescribe, I want an initial a series starting at 1, but then you evaluate in this system, you replace everywhere y0 by 1, the system simplifies, and you see that since all these three polynomials must vanish, y1 to the square must be equal to 0, so you need to have, you are forced to take y1 is equal to 0, then all this disappears, and it remains that only a single equation, 2y2 to the square plus y2 must be equal to 0. There are two solutions. y2 is equal to 0, which will eventually lead to the constant solution y is equal to 1, and y2 equal to minus 1 over 2, which leads to the cycloid. So we recover what we have seen so far. Okay, and in general, here, of course, we know the example. We know I knew we could stop at P2, but how do we know that? And the answer is we don't know, actually. We don't know that precisely, but Denef and Lipshitz give us a bound. What they tell us, over this example, the numbers depend on the example, but over this example, if you apply their formula, that you can take beta and delta equal to 5. And that means that, well, if you don't know in advance the example, you will have to go up to from P0 up to P4, plug, do exactly the same thing as we did. And if there is a solution to this system, then the solution will be, you will be able to prolongate it up to any order. So the theorem tells us that if you find y2, y3, and y4 such that, so 1, 0, y2, y3, y4 annihilate this system, then there exists a formal power series y double bar starting with these 5 initial values. If you provide, if y2, y3, and y4 are precise numbers, the solution exists and is unique. But in general, this is not what we want to do. In general, what we want to have parameters. And we would like to say, okay, and what about to say, and if y2 is different from, or y3 is different from this, or if you want to put parameters in the problem, then the problem becomes much more complicated, and you have existence but not uniqueness. And it's a tough problem, but they address it also in their paper. I will not enter this. Next example, because we are still the same example. Remember, at y0 is equal to 0, we have no formal power series, but we have a formal Puiseux series. And actually, we can use Denef and Lipshitz result to find the Puiseux series. You just perform a change of coordinate over the Brachistochrone ODE. I have not written the change of coordinate, but it's not very complicated. And you can transform, assume that you suspect the ODE to have a formal power series in x to the 2/3. Then you perform a change of coordinate, you get a new ODE, which is this one, and this new ODE has a formal power series at 0, 0, at y0 is equal to 0, and x0 equal to 0, if and only if the Brachistochrone ODE has a Puiseux series solution in x to the 2/3. So if we apply, I have done it before the talk, if we apply the Denef and Lipshitz result over this example, again we have beta and delta is equal to 5. We compute P0, P1, P4. I will not write them all because the formula are too long. I've just computed these ones. So P1, you have P and P prime, you differentiate the ODE. You rename y into y0, y prime into y1, and so on. You evaluate at the expansion point x is equal to 0 and y0 is equal to 0. Everything disappears but two monomials. And then you find out that y1 must be equal to the cubic the cubic root of 9/4. And if you go on like that, you have painful numbers, but you can compute them all. So if you continue, you find out that the system has a solution, and you know then that the Puiseux series exists, and moreover, when you have the formal power series of the new ODE, by applying the inverse change of coordinate, you get the formal Puiseux series of the Brachistochrone ODE. So it's a very interesting result in this Denef and Lipshitz paper. Okay, so I'm really advertising for their paper, but yeah, it's a good thing. So I've explained to you the lemma 2.2 and 2.3 without giving you the formula, but you can see the formula in the paper, and they are used to prove many of the results, including an approximation theorem, which is this one in their paper, theorem 2.10. Let's read it together, but because this is a transition to topical differential algebra. So let f be a characteristic 0 algebraically closed field. And for instance, you could take for f the algebraic closure of the field of the rational number. It would be in the hypothesis. Or even a real closed field. And suppose that for any beta there exists, so we have n variable here. So we have n initial value encoding formal power series. Assume that p of x, p evaluated over this initial value, well, for each beta, you have a solution to this system. Not necessarily the same one which is prolongated. You just need to have at least one solution, whatever the number of times you differentiate. Then there exists a formal, real formal power series solution for the ODE. We have to erase this modulo x to the beta. There is no modulo x to the beta here. Amir, I will send you fixed slides because this is false. It's p of x double bar 1, y double bar 1, y double bar n equal to 0, modulo nothing. Theorem is not true for any field. It is false if you take for a field r of t being a variable. It's a weird example in the paper, relying on former paper of Denef and Lipshitz. It's impressive. In the PD case, so here we are in the ODE case. In the PD case, the theorem is true for the field of the complex numbers. It's not true for the field of the algebraic closure of Q. You need to take the field of the rational number, and it's false for the field of the real numbers. So it's not at all an obvious theorem. And actually, let's move to typical differential algebraic geometry. If we, so for instance, Aroca, Christian Garay and Denef and Toghani in 2016 published a very interesting paper on the fundamental theorem of tropical differential algebraic geometry. And in this paper, there is an hypothesis that many people, including them, I think, do not like, but they could not avoid it. A painful hypothesis on the base field. And if this theorem had been true, it's almost the right tool we would have needed to drop this hypothesis. This is a relationship with the tropical differential algebra. Let us describe this now. So, tropical differential algebraic geometry is, as Denef and Lipshitz, is concerned with by the existence problem of formal power series solution with prescribed, not initial values, almost, prescribed supports. So what is the support of the series? Y bar, it's just the set of the, you explain which are the initial values which are going to be 0 and which one are not going to, are not allowed at all to be 0. So some are prescribed to be 0, some are prescribed to be non-zero. So the support is a set of indices such that initial values number I is different from 0. So the fundamental theorem assumes a few things. You need sigma to be a differential ideal in the differential polynomial ring. If you don't know what it is, it's not a big deal. It's not very important for this talk, but I need to mention it. A set is a differential ideal if whenever you have a differential polynomial in the set, you have all its derivatives also. It's an infinite set. So in order to be true, you need sigma to be a differential ideal, but it's not very important for this talk. And 2, the base field must have characteristic 0. It must be algebraically closed. I forgot the hypothesis. And it must be uncountable. This is a painful hypothesis. This uncountability hypothesis is very strong. If you recall the Denef and Lipshitz theorem 2.10, the base field F could have been the algebraic closure of the rational numbers, but this field is countable. So the theorem 2.10 proves the things for in much more general fields than the fundamental theorem of tropical differential algebra. What can be done over this hypothesis? So it's not very difficult to relax it to a countable field, but even doing this, the only thing we could do is to assume that, okay, it is countable, but you need anyway an infinite transcendence degree, infinitely many variables, an infinite transcendence degree over the field of definition of sigma. So you need to have infinitely many transcendental numbers in your field. And once again, the algebraic closure of Q is much nicer since you don't have this hypothesis. It has a transcendence degree 0 over the field of the rational numbers. So even with this relaxation, we don't get something as nice as the Denef and Lipshitz theorem 2.10. Let's state the tropical differential, the fundamental theorem. So let sigma be a differential ideal, f be an uncountable algebraically closed field of characteristics 0, then you have this equality. It's a theorem of a fundamental nature. It does not give you any formula that you can use for computation. But it is related to all the problems we had from earlier. So let's explain it. So on the left-hand side, it's the simplest. The solution of sigma are formal power series. So the support of the solution of sigma it's a set of supports. So it's a set of integers. It's a set of the supports of all the formal power series solutions of sigma. Strictly speaking, if you think quickly, you will wonder because we should not have simply supports but tuples of supports with tuples having n coordinates because we have n unknown functions. But I will not mention tuples of support. I will always assume for legibility that we encode everything with a single support. We can always do that through some encoding. So that makes statements much simpler. So I should talk about tuples of supports, but I will not. I assume that my tuples of supports are just supports through some encoding. So the left-hand side of this equality is clear. Now let's have a look to the right-hand side. So a support S belongs to sol of drop of sigma if and only if f, we can define it sol of drop of p for a single differential polynomial p. So S belongs to sol of drop of my differential ideal sigma if and only if S belongs to sol of drop of p for each p in sigma. So we have to define this object. So it's a bit technical, but I could not avoid that. So you have to decompose the polynomial, the differential p as a sum of monomials, and consider y bar as a generic series having the support S. We have to define the valuation of a monomial m at S. This is very classical. I just recalling it here, but the definition is very classical. If your monomial m, one of the monomials of P, vanishes at y bar, then the valuation of y bar is equal to 0. It is equal to infinity by definition. And if the monomial does not evaluate to the 0 series, then it will start with C0 x to the k plus C1 x to the k plus 1 for some k, with C0 different from 0, and then the evaluation is just the exponent k. So now I can explain the definition. So a support S belongs to sol of drop of P, P being my sum of monomial M1 plus M2 plus MR, if and only if one of the two conditions applies. possibly all monomials disappear, evaluate to 0. This is the first condition. And second condition, there must be at least, well, let's read it. There exist two indices J and K between 1 and R. So J and K are indices for monomials. So there must exist two different monomials, such that those two monomials have the same valuation at y bar, and this valuation is the minimum of all the valuation of all the monomials m1 up to mr at y bar. And somehow, well, it's a bit technical written like that, and I'm not possibly very clear in my explanation, but it's quite obvious in some sense. What is clear is that if y bar is the solution of your differential polynomial, obviously the condition 1 or 2 must be satisfied, because the condition 2 explains that how to say that? The condition 2, if one monomial evaluates to a series which is not 0, it must be annihilated by the series obtained by another monomials. And in particular, this must be true for the lowest terms. It is just what this second condition expresses. And so then the theorem becomes a bit weird. At the beginning, I thought it was false, actually. I tried to prove it was false, and actually it is true. But the first time I saw the theorem, I thought it's not possible, it cannot be true, because it's a bit weird. So you have an inclusion which is clear. So the fact that Solovstrop of sigma is included in the support of all the solution of sigma, it's actually obvious. But the other inclusion is not at all obvious, because, well, condition 2 just tells you that possibly there could exist initial values, but they don't give you initial values, and you have no constraint on the initial values. And it's not clear at all that this condition actually is sufficient to guarantee the existence of a formal power series solution. So I'm looking at my time. I have, I would say, 3 minutes or something like that. So that should be okay. I'm almost done. So the proof of the fundamental theorem, you have two proofs in the paper, two important proofs. And one of them is an approximation theorem, a bit like the theorem 2.10 of Denef and Lipshitz. And this is a way to state it. It is not the way it is stated in the paper, but you could state it like that. I've put in pink what is not the part of the statement that you do not find in Denef and Lipshitz theorem 2.10, which explains why the difference between the two, the assumptions. So let S be a support, F0 be a characteristic zero field, and P a differential polynomial. Suppose that for any exponent beta there exists for any beta the prolongated system has a solution modulo x to the beta. Then there exists formal power series with double path.
Francois?
Yes.
I think there is a problem with your microphone, or perhaps it's my case. I do not know.
You don't hear me?
Do you have the same problem? No, it's okay. I apologize.
No. So you stop. You could not hear me for a while?
Just when you start to talk about this theorem, before that was okay.
Okay, let me just read it at the beginning. In pink, you have the part which you don't find in the Denef and Lipshitz theorem 2.10, which shows the difference between both and which explains why the conclusion is not the same. By the way, there is the same mistake at the end, which is this one. There should not be any modulo x to the beta at the end. I will fix that also I will send you another version of the slide with this being fixed. So if for any beta you have the prolongated system as a solution, then there exists formal power series. So y bar 1, y bar n being compatible with the support, then there exist two solutions, y double bar 1 up to y double bar n, compatible with the support, but with their coefficient being in an extension field of the field f0, and then you need either an uncountable field extension or an infinite transcendence degree over f0, and you have such a solution. And unfortunately, we spent quite some time trying to see if the proof of Denef and Lipshitz could apply as is for the fundamental theorem of tropical differential algebra. And the problem is, it looks like not. The proof does not survive to the with support S requirement, which does not mean that the theorem does not survive, but actually the proof of Denef and Lipshitz does not survive, unfortunately. Otherwise, we would have a much nicer version of the tropical differential algebraic geometry fundamental theorem. So let me conclude. So my own relationship with all of this. So I was involved with the fundamental theorem of tropical differential algebraic geometry could be generalized to the PDKs, and I worked with Sebastian Falkensteiner, Christian Garay, Mercedes Ayesh, Marc-Paul Norman, Denef Toghani in 2020-2021 on this. And I spent quite some time on this approximation theorem issue. That's why I made the talk on this. You may have the feeling that the relationship between the tropical differential, the fundamental theorem and numerical integration is not very tight. It's a bit true, but remember that even the Denef and Lipshitz theorem is all about, well, you could not see it because I have not explained the detail. It's quite a lot concerned with evaluation and things which annihilate and do not annihilate. So we are not that far from their paper, and their paper is definitely related to numerical integration. So I think that there might be a much stronger relationship with numerical integration than the talk let us think. Just a few words about the differential algebra package in Python. It is freely available. It works over Linux. It should not be any problem for you to use it. For macOS, it should work, but I was reported by some people that it works. For Windows, nobody tested, but I think I have to do some stuff on my side to make it easy to use. So in Windows, let me say in a short while. So it's very easy. In Python, you run such a command. And the code source and worksheets, in particular related to the brachistochrone ODE, can be obtained on this URL. And you have everything is open source, and you can have everything. And there are some PDF documentation there also, even from a mathematical point of view. It's over. My talk is finished. Thanks a lot.
Okay, thank you, Francois, for your interesting and informative talk. Could you please give some words about the functions and difference between the Python and Maple package of differential algebra? Which kind of function you have added with respect to the Maple package to this Python package?
I stop share screening so that you should see me better, and I see you better also. So in principle, the Maple package, differential algebra, and the Python package, they rely over the same C code. They have all the code inside is in common. It is a C library. So in principle, you should have the same code in Maple and in Python. But the Maple, the version of the C library in Maple is much older than the one in Python. I am discussing with MapleSoft to update this library so that in principle we would have the same the same C library behind, so the same library performing the computation, but then you still have to put some functions exist in Python and not yet in Maple, and they would have to be translated, but that should not be a big deal because they are just interface functions. So the sort of things you find in Python and not in Maple. So there is some stuff on Denef and Lipshitz, but it is not yet integrated in the differential algebra package. It's on a separate package for the moment, but it's already available on the website. There is for integrating ODEs. It's difficult to explain just by waving hands, but when you have a linear ODE, say with a constant coefficient, it's very easy to convert it into an integral equation. You factor the d over dt differential operator. If you have a linear ODE with constant coefficient, it's just it's very easy. And when the d over dt is factored, it's very easy to integrate. And for we have an algorithm that we developed here at Lille in 2016, and which works also for in the non-linear case. Of course, the result is not as nice, so it's a sum, it's a decomposition of. We managed to factor the d over dt operator up to some point, and that permits to transform, in some cases, non-linear ODEs into integral equations, or in integral differential equations in the general case. So you have stuff like that, and there is no other major algorithm difference between both algorithms. But even the Rosenfeld-Grobner elimination algorithm is better in the new C library than the old one. It was improved also quite a lot recently.
Okay, thank you. So if there is any question, I think you are able to turn on your microphone and ask your question directly to Francois.
Amir, can I have a question?
Yes, please.
Thank you. Thank you, Francois, for interesting lecture. I have a question. Is there any notable result concerning the case that we are seeking for those initial conditions which provide real analytic solutions instead of formal power series ones?
You mean the convergent series?
Yeah, of course.
Yeah, and in the real case, there are results in the Denef and Lipshitz paper. Mostly, well, what you know is this. Let me share. I share my screen again. Okay, this result of Denef and Lipshitz. You have the no, not this one. I'm sorry. This one, this existence result here. Actually, they managed to basically they prove that once you have passed the bound beta, you have explicit formula for the next coefficient of the series. So say y to the 10 is equal to rational fractions, and all the issue about the polynomial system is all about they don't want the denominator of the fraction to be 0. But so somehow, if you let me do it like that with this slide, if you solve this system, and if you have a real solution, obviously it will be prolongated as a real series. And that answers about the real part. And about the convergences, I remember in the Denef and Lipshitz paper, there are undecidability results for a convergent series. They say that it's false also, or it does not work either if you require the series to be convergent, or there are many things which do not work. And so And you have this, even for the PDE case, the non-existence problem, when they show that there does not exist a solution, and I will have to read the paper. I remember that they mentioned the fact that, well, and the series would be, convergence is not, convergence is covered also with negative results. So mostly you have negative results. I don't have in mind results where you have will have something positive and well, my answer is not very clear. I'm sorry, but there are results in the Denef and Lipshitz paper, right? They are difficult to state here without stating the whole theorem.
Okay, thank you.
Any other question? If anybody has a question, can unmute his or her microphone and ask the question. No question? Okay. Thank you again, Francois, for your nice talk, and I enjoyed it.
Thanks.
And I wish a nice
covering so many topics. And I will send you the fixed slides because
thank you very much. I will send it to okay, thank you anybody to attend this talk, and I wish you a nice evening.
Thank you very much for listening to the talks. It's a pleasure also for me to talk like that to all of you. Thanks a lot.
You are welcome. Bye-bye.
Bye.